Hello students, so today we are going to discuss about redox reactions as the basis for titration. So first thing first, what is titration? So in laboratory you have to do three different type of practicals, mainly three different type of practicals. First is volumetric titration, second one will be inorganic qualitative analysis, and third one will be organic qualitative analysis. So first practical, that means volumetric titration. In these type of practicals you will be provided with two different chemicals and you already know both of them. That means we know about the chemicals and we have to find their concentration. One of the chemical is already known with their concentration, second one will be unknown concentration. As for example, HCl and NaOH, hydrochloric acid and NaOH, sodium hydroxide. So let's say we have known concentration of HCl and it is 0.1 molar, and you have unknown concentration of NaOH, and our target is to find concentration of NaOH using HCl. And for that we can use the indicator phenolphthalein. Now what is indicator? So generally indicator changes color with changing pH. So phenolphthalein gives pink color with basic medium and it is colorless with acidic medium. So method of practical is, first we will take some known quantity, to be exact 10 milli of unknown concentrated NaOH solution in flask. Then we will add few drops of phenolphthalein, so solution will become light pink. And then drop wise addition of HCl will be added in the beaker or in the flask. So when color changes from pink to colorless, we have to stop addition of HCl and then measure the quantity of HCl added in the flask. From the concentration added, from the volume added of HCl into the NaOH, we can find the concentration of unknown NaOH. We will discuss about these practicals in detail when we do it in practicals. So let's proceed to our topic. So in acid-base system we come across a titration method for finding out the strength of one solution against the other using a pH sensitive indicator. Now pH sensitive indicator, that means it will change its color based on pH. Similarly, in redox system, the titration method can be adopted to determine the strength of reductant or oxidant using the redox sensitive indicator. Now, just like pH sensitive indicator, redox sensitive indicator will change the color based on the change in reduction or oxidant concentration. The use of indicator in the reduction titration, redox titration is illustrated below. Now we have three different type of redox reaction which requires different type of indicator. First one, it is self indicator. That means one of the compound has comparatively strong intense color so that it can act as indicator. So first one, in one situation the reagent itself is intensively colored. Example, permanganate ion. Now permanganate ion gives intense color in very small quantity. As mentioned here, MnO4 minus act as self indicator. The visible endpoint in this case is achieved after the last of the reductant, as for example Fe plus 2 or Cr2O7 2 minus, is oxidized, and the first lasting tinge of pink color appears at MnO4 minus concentration as low as 10 raised to minus 6 moles per decimeter cube or 10 raised to minus 6 moles per liter. So 10 raised to minus 6 moles per liter, that means 0.000001 mole per 1 liter of solution. That means it is very low quantity. In such a low quantity, still permanganate ions can give pink color. So this ensures the minimal overshoot in the color beyond the equivalence point, the point where the reductant and oxidant are equal in the term of their mole stoichiometry. Now overshoot, that means slightly more quantity of KMnO4 is required to get this color, but it is a very negligible amount. We can easily ignore such over addition of the KMnO4. Now second method is where reactants are not self indicator. So if there is no dramatic auto color change, there are indicators which are oxidized immediately after the last bit of reductant is consumed. So when reductant is consumed, then indicator will start participating in the reaction and indicators will give us change in colors. And that's why it producing a dramatic color change. The best example of afforded by Cr2O72 minus. So dichromate ions, which is not a self indicator but oxidizes the indicator substance diphenylamine just after the equivalence point to produce an intense blue color and thus signaling the end point. That means when reagents are not self-indicator, then we will use indicators, just like we discussed in first practical HCl NaOH. We use phenolphthalein. Similarly, in this case, we will use diphenylamine. And because of presence of diphenylamine, our solutions will change the color. Third one, it is slightly different than the second one, but it has similar trend. So there is yet another method which is interesting and quite common. It is restricted to those reagents which are able to oxidize I minus ion. And for example, Cu plus 2. When Cu plus 2 reacts with I minus, it produces Cu2I2 and I2. That means iodine. So this method relies on the fact that iodine itself gives the intense blue color with starch and has a very specific reaction with the thiosulfate ion, which too is a redox reaction. So you in this reaction you will get two different type of redox reaction. First, as mentioned here, Cu2 plus I minus, they will participate in redox reaction, and later produced I2 in the first reaction will be used in second reaction. So I2 with S2O32 minus produces 2I minus with S4O6 2 minus. So I2 through the insoluble in water remains in the solution containing Ki as Ki3. So Ki plus I2 produces Ki3. And now on the addition of starch after the liberation of iodine from the reaction of Cu2 plus ion on the iodine ions, the intense blue color appears, and this color disappears as soon as the iodine is consumed by the thiosulfate ion, and thus endpoint can easily be tracked and yet rest in the stoichiometric calculation only. That means from the first measurement of the quantity added in the solution, remaining things are we have to follow the balanced chemical equation. From the balanced chemical equation we can find the masses to neutralize each other, and from the masses we can find the concentration. We will discuss about these type of practicals in detail in laboratories. Now let's move towards the second point. So today's second point is limitation of concept of oxidation number. Now it is a very short topic and nothing much is mentioned here. So let's talk about it anyways. So as you have observed in the above discussion, the concept of redox processes has been evolving with time. That means in earlier times we thought differently and then we have some developments in it. So this process of evolution is continuing. That means still we have to develop something in it, and the oxidation number methods are not perfect yet. In fact, in recent past the oxidation processes are visualized as decrease in electron density, and reduction processes are increase in electron density around the atoms involved in the reactions. And right now we also know that, as for example, if we talk about the water molecule, we assume hydrogen as a plus 1 ion and oxygen as minus 1 ion. But we know that it is not true. In case of water molecule, hydrogen and oxygen both are present as atoms attached with each other, they are not ions. But still, according to oxidation reduction method, we assume that they are present as ions. So last topic of this unit will be redox reaction and electrode processes. Now basically electrode processes has a dedicated unit in standard 12. So we will discuss it in detail in standard 12 in unit electrochemistry. But here some basic information is mentioned for it. So let's discuss it anyway. So experiment corresponding to reaction 8.15, that means in earlier topic of this unit, topic competitive electron transfer, we discussed this practical. And in this practical we followed this reaction where Zn plus zinc solid is oxidized in Zn plus 2 and copper ions are reduced in metallic copper, as we can see in this beaker. So we have zinc rod dipped in copper solution, and as the time passes intensity of color reduces and we see the reddish color developing on the zinc rod. So as we move forward, almost blue color of the solution will be removed and we can see a red colored layer on the surface of zinc solid. So what reaction is going on here? So reaction is blue color of solution is because of Cu plus 2 and Cu plus 2 is reduced into copper metal. So that's why Cu plus 2 are removed from the solution and that's why blue color are reducing. And reduced metal will deposit on the surface of zinc rod and that's why we see reddish color developing on the zinc surface. At the same time, zinc metal is being oxidized into Zn plus 2 ion and it will be dissolved in the solution, and later we have zinc solution and that's why it is colorless. In short, electrons will be transferred from zinc to copper plus 2 ions and that's why later you will get zinc ions and copper solids. So in this reaction, zinc is oxidized to zinc ions and copper ions are reduced to copper metal. And it is because of direct transfer of electron from zinc to copper ions. Direct electron transfer, that means zinc atoms and copper ions will be in contact with each other and electrons will be transferred from zinc to copper directly. So that's why it is mentioned as direct electron transfer. But what happened if we separate these two from each other and then still we can proceed to electron transfer? That means what happened if we do indirect electron transfer? And to do so, we have to separate both of the compounds from each other. That means zinc metal and copper solution. We have to separate them out as we can see in this beaker. In these two beakers, we have zinc plus 2 solution and zinc rod dipped in it. On the other beaker, we have copper solid and copper 2 plus solution. So two different beakers, two different solutions with two different metal rods. And we have oxidized form and reduced form of both of the metal at the same time in contact with each other. So to separate them out, we will separate them with a slash like this. Okay, so it represents zinc reduced form and oxidized form. They are in contact with each other. Similarly, we can do so for copper as well. That means in this case we have copper and copper oxidized form in contact with each other. So this is called redox couple. Now as we can see, our target was to separate out both of them. That means zinc rod with copper solution. Now they are separated from each other. So direct electron transfer, it is not possible now. So what happened if still same reaction is going on? On the left hand side of the beaker, that means in, let's say, beaker A, we can get oxidation reaction of zinc. That means zinc metal, which is present as solid rod, will dissolve in solution as Zn plus 2 ion. At the same time, it releases 2 electron. Now this 2 electron will travel through this conducting wire towards the other end of the instrumentation, that means on the surface of copper rod. So this copper rod contains metallic copper and solution contains copper ions. Now these copper ions will feel attraction towards this electron and reduction reaction takes place as it is mentioned at the bottom. So copper will turn into metallic copper by accepting the electron released from the zinc via indirect electron transfer. Because of that, as we can see, we can get flow of the electron on this conducting wire which attaches these two metal rods with each other. These metal rods are known as electrodes. And when we attach this instrumentation, it will behave as cell. Cell, that means which produces electricity. As for example, we can take example of our car batteries or phone batteries. When we use the headlights of car, we are actually using the chemical reaction to produce electricity. Our batteries do chemical reaction and produce electricity. But when we run the car, it has some mechanical parts which produces electricity called dynamos. So dynamos will rotate with the car engine and it will produce electricity. And with the help of electricity, we can recharge the car batteries. Similar situation can be observed in phone batteries. When we use the cell or when we use the device, it uses chemical reaction to produce electricity, and when batteries are discharged, we put phone on charging. It uses electricity to reverse the chemical reaction. And same thing is going on here. Right now, because of two different chemical reactions, on the left hand side beaker, reaction with zinc metal will be oxidized into Zn plus 2 and it releases 2 electrons. Now this released electron will travel on the other end via this conducting wire, and on the other hand copper plus 2 will accept this 2 electron and it will turn into metallic copper, and electron flow will be from zinc to copper, and that's why, as mentioned, electron flow is from this direction, from anode to cathode. Oxidation reaction will proceed on anode and reduction reaction will proceed on cathode. Now electron flow, it is flow of negative charge, and current flow, that means flow of positive charge, and that's why they are opposite to each other. And these reactions are mentioned at the below as well. And to complete the circle, we have salt bridge which attaches both of these solutions. So usually salt bridge is filled with KCl or ammonium sulfate with boiled with agar agar to turn into jelly like substance by cooling it, and its main function is to transfer of ions from one end to other end, or you can say that to complete the circuit, because this is a cell and we need to complete the circuit to get electrons flowing. And by putting ammeter or galvanometer attached with this wire, we can see the electron transfer, or we can see the flow of electron via electricity flow. And this type of cells are called Daniell cell or galvanic cell. And as soon as we switch on the device, we can see the following observations. So first, transfer of electron now does not takes place directly from Zn to Cu2 plus, but through the metallic wire connecting two rods, as it appears from the arrow which indicates the flow of current. Second point, the electricity from the solution in one beaker to solution in the other beaker flows by the migration of ion through the salt bridge. We know that the flow of current is possible only if there is a potential difference between the copper and zinc rod known as electrodes. Potential difference, that means we can say that internal energy difference. As for to understand it, let's take a simple example of heated substances. Suppose you have two different blocks of metal, one having 100 degrees Celsius temperature, second having 50 degrees Celsius temperature. So when we put these two in contact with each other, metal block with higher temperature will decrease its temperature by transferring heat to the lower temperature solid. So temperature of lower temperatured block will increase. So similar situation will be observed here when we have higher internal energy and lower internal energy containing two electrodes. Energy transfer will take place. In this case, energy transfer will take place as electrical energy. The potential associated with each electrode is known as electrode potential, and if concentration of each species taking part in the electrode reaction is in unity, that means if molarity is 1 molar, and if gases are used, then pressure of gas should be 1 atmospheric pressure and temperature should be 298 Kelvin, then all of these conditions are known as standard condition, and at that time the electrode potential will be known as standard electrode potential. By the convention, the standard electrode potential of hydrogen electrode is considered as 0.00 volt. Now it is considered. What it means? To understand what it means, let's take an example of two different masses. Let's say we have A and B, two different masses, and we don't know the value of A or B, but we have a weight balance, which can give us the difference of weight between these two, and let's say difference between these two is 5 kg. So it means either A will be 10 and B will be 5, or it may be 15 and 10, or it may be 5 or 0, or any other value which has difference of 5. We cannot say what is the value of A and what will be the value of B. So how can we tell what is the value of A and B? For that we need a known weight. As for example, let's say we have a weight C and the value of C is 3 kg. So when we attach A with C in a weight balance, let's say difference is equal to 7. So we can say that if C is equal to 3 kg, then A must be 10, and if A is 10 then B will be 5. So simple thing, we cannot measure the absolute value of the potential of the electrodes, but we can measure the difference just like mentioned here. So that means if we have zinc and copper rods attached with, as we discussed in the example, we cannot find the value of potential of zinc or copper. But what we can get the difference of both. So to know the value of zinc and copper, we will assume the potential of hydrogen electrode is 0. Now we can attach either zinc or copper with the hydrogen, and then we can find the difference, and from the difference we can find the absolute value of zinc or copper. So that's why for hydrogen it is considered 0. The electrode potential value of each electrode processes is a measure of the relative tendency of the active species in the process to remain the oxidized or reduced form. A negative E naught value means the redox couple is stronger reducing agent than H plus H2 couple, and a positive value, that means it is weaker reducing agent than the hydrogen. We have multiple different type of these type of redox couples, and they are mentioned in the following table. And same table will be mentioned in standard 12 unit electrochemistry, and we will discuss about these topics in detail in that unit. So right now let's talk about this table in short. So all of these reactions are mentioned as reduction reactions. As we can see, reaction of oxidized form accepts electron, it turns into reduced form. So all of these reactions are reduction reaction. As for example, F2 will gain the electron to turn into F minus. So these reactions are reduction reaction, and that's why these potentials are known as reduction potentials. So as we move from top to bottom, values of reduction potentials decreases, and decreasing value represents increasing strength of reducing agent, and as we move from bottom to top, it represents increasing strength of oxidizing potential. All of the values are mentioned here, you can check it yourself, and we will discuss about this in detail in standard 12. Now our unit is complete, so in next lecture we will discuss about some of the reactions for balancing which are mentioned in the exercise. So check it yourself. If you find any difficult reaction, then feel free to ask. We will discuss those reactions, and if I do not get any questions from you, then I will choose the randomly, and we will discuss about the two different methods we learned earlier.